Okay, good afternoon. Today we will look at, or we'll begin working with logic gates. So, first up is the logic gate known as NOT gate. So these gates, as the term suggests, gate as the term suggests, it's either a pathway, it's open or closed, right? In electronic design or in logic design, these serve several functions. And these functions are primarily three of them. First one is the inverter. Second one is summation. The third one is multiplication. So it performs the mathematical functions of addition, multiplication, and inversion. Okay. So we look at first these three gates, see how they're implemented in digital logic circuits, and then we'll look at other gates that serve some special functions. Okay. Now, we are using binary math or logic math, which is not exactly the same as the arithmetic that we have learned. Okay. Not stands for, or not stands for, basically refers to inversion. So in logic circuits or logic design, it stands for an inverter. Okay. Inverter, as the name suggests, would give you an output result that is the opposite of the input or inverted output. Inverted output. Gate or the function of the gate is defined or is presented in a table. The table is known as a truth table. For the NOT gate, shown right here. A is the input to the gate, and the output, we receive something known as A naught. So the bar that you see on top is referred to as naught. And so the way we would say this is A naught. So a NOT gate is simply an inverter gate. If you apply an input A, the output is A naught. If you apply a 0, you'd obtain a 1. If you apply 1, you obtain a 0. And in many cases, this is a very important function because this allows us to implement logic circuits that can perform a variety of functions. Okay. We are going to use these gates as building blocks to create other larger logic circuits. Symbol for this inverter is like a diode. It's an arrowhead, it's a triangle with a bubble. And this bubble indicates inversion. Okay, bubble indicates inversion. So anytime you see a bubble on a gate or a logic circuit, it simply means opposite or inverted. Okay. So again, NOT gate has a single input. The output is basically the inverted or the opposite of the input. And because it's a single input, you can only have two possible outcomes, 0 or 1. If you apply 0, output is 1. If you apply 1, output is 0. Then we have the AND gate. In terms of English language, AND would simply mean you're adding it up, right? AND would simply mean you're adding it up. Here, it actually represents multiplication. Okay. If we say 1 and 2, we would typically just mean 1 plus 1, we say 2 and 3, we might say 2 plus 3. But here in logic design, the AND means mathematical multiplication. Okay, mathematical multiplication. And an AND gate symbol is represented here. 2 inputs and 1 output. 2 inputs and 1 output. A, B, because we have 2 inputs, now we have four possible combinations of input. 0, 0, 0, 1, 1, 0, and 1, 1. And if we take multiplication, we simply take multiplication, then 0 times 0 would give us 0. 0 times 1 would give us a 0. 1 times 0 gives us 0. And only 1 times 1 gives us 1. Okay. Logically, we write C, the output, as A and B. Arithmetically, we would state it as A times B. Logically, we would write A and B. So C is equal to A and B. All right, let's take a pause. What do you think over that? Let me know if you have any questions. Does this make sense so far? Okay. You have a question? Okay. So C and B. For an AND gate, the output is high only when both inputs are high. Funny statement. Again, for an AND gate, the output is high only when both inputs are high. And high in terms of circuits would simply mean if it's a 5-volt circuit, typical digital circuits are 3.3 or 5 volts. The output would be plus 5 volts only when both inputs are at plus 5 volts. For any other combination, output would be 0 volts. Okay, so in terms of circuits, it would simply mean output is plus 5 volts only when both inputs are plus 5 volts. Okay. And then we have, I'll come back to this later. We have an OR gate. Okay, OR gate. Or in the word OR in the English language simply means either, right? It's either A or B, not both. But in logic design, the OR function represents arithmetic addition. Okay, so the OR function is arithmetic addition. So in logic design, if you have a OR gate or a 2-input OR gate, the output would be C equals A plus B, meaning both the inputs. The sum of the 2 inputs. Yes, sir. So binary math. So question being asked is, why is the output of 1 and 1 equal to 1? So yes, binary math, we saw 1 and 1 would be, sum would be equal to 0 and carry would be 1. So that's a very good question. But here, that represents the carry bit. But in logic design, it simply means that the output of a OR gate would be high when a single one of those gates goes high. Sorry, not gates. Even a single input goes high. So when either one of the inputs is high or logic 1, the output is 1. Okay, and that is the definition of logic OR. Again, it's not a mathematical summation, it's a logical summation. Okay. So it's, again, it's one of the reasons I go a little bit slower is because this is completely new and very, I wouldn't say difficult, but slightly different than, so our thinking needs to be adjusted a little differently. So again, the output is high for any one of the inputs going high, and that is logical OR. Logically, it's represented C is equal to A plus B. So logical summation. Okay, logical summation. Now, all three of these, the NOT gate is a single input, the AND and the OR gate are two inputs. We can have multi-input gates, meaning if you have multiple transistors in your circuit, you can have an AND function for all those inputs, 3 inputs, 4 inputs, 5 inputs. Doesn't matter how you design it, but you can have multiple inputs in there. But the function remains the same. Okay, so if you have a multi-input OR gate, the output would simply be like D is equal to A plus B plus C. The end result would simply be the same. The output would be high or logic 1 if even a single input is high. The rest of them could be 0. It would simply be 0 plus 1 plus 0, 0, 0, 0. The output would still be 1. Okay, so multi-input gate function still remains the same. A plus B plus C plus D plus so on and so forth. And that I will go back to this slide where we have a 3-input AND gate. So here you have a 3-input gate. The function remains the same for an AND gate. It is A and B and C. Output will go high only when all inputs are high. And so D is referred to as A and B and C. If you have 4 inputs, A and B and C and D, 5 inputs and E and F, so on and so forth. But the resulting truth table is simply that the output is high only when all inputs are high. So it doesn't matter how many inputs you have. Okay. All right, let's take a pause. Let me know if you have any other questions. Yes. I believe, so the question being asked is how many input gates we have in the lab. I think all the gates that we use in the lab are 2 input gates, as far as I know. They're all 2 input gates. There is one in there that's a 2 input NAND gate, I believe. So, and we'll talk about that just in just a little bit. Let's see. OR gate. Why do I have these mixed up? Let's see. We have OR, logic OR. Okay, there we go. So I had this here. My printout and my slides are kind of mixed up a little bit. That threw me off. So this is the 3-input OR gate. Okay. I think I already spoke about this on the previous page. 3-input OR gate. So the answer is A plus B plus C. Output goes high when even a single input is high. So this is a 3 input and you can have a multi-input gate. Just as an example, we can use these gates, let's say some sort of temperature control system or pressure, humidity, alarm system, meaning if even a single door opens, a beep would sound. That's where you would implement these kind of logic functions. And so if you had an OR gate with multiple inputs, each input is connected to a door, right? When the doors are closed, everything's logic 0. When door opens, let's say there are 10 doors, so you have 10 input gates. When a door opens, that goes high. When that goes high, the output goes high. And so a chime or a beep sounds. Or if you set an alarm would go off. Does that make sense? That's a very simplistic example of where you would have this kind of logic circuit design. Okay. All right. So from OR gate, we go to two of the other important gates, which is the NAND and the NOR. Effectively, you're adding a NOT gate to a AND gate and a NOT gate to an OR gate. So the output is now flipped or inverted. So you take an AND gate and you connect a NOT gate to its output. Then the combined output is A and B NOT. So the way we would pronounce this is A and B NOT. The output of a NAND gate is A and B NOT. Okay. And the truth table for this is the exact opposite, of a AND gate. Right? AND gate is A and B. So the output was high only when both inputs are high. NAND gate is the exact opposite. And so in the NAND gate, if you have right here A, B, and let's say output is C. If A and B are 0, 0, what is C? 0 and 0 should be a 0, then you NOT. And so output is, I heard 1 and I saw rumblings of 1. How about for 0 and 1? Zero and 1 would give you 0. You invert it, so 1. Yes, that's correct. 1 and 0. 1. How about 1 and 1? All right. So for a NAND gate, output is always high, except when all the gates are high. In other words, output goes low only when all inputs go high. Okay, that's NAND gate. Yes, take a pause and you think over that. Let me know if you have questions. All right. Time are we at 12:30? Yes. Yes. So the question being asked is, we have the AND first and then the NOT. The answer is yes, because we are creating a 2-input gate, 2-input NAND gate. Otherwise, we'd have to have 2 NOT gates at the input of the AND gate. And even then, I don't know if that would be an AND or not. So the NOT is always after. So we attach the NOT gate at the output of the AND and the OR gates. Speaking of which, that's the NOR gate. Oh, one more thing. See this bubble? So the symbol is simply an AND gate and a bubble at the output. So anytime you see a bubble, that bubble means you're inverting or you're flipping the output. All right, NOR gate. NOR gate is the same as the NAND. You have a NOT gate attached to the output of the NOR gate. I mean the OR gate. So OR and NOT gives us a NOR gate. All right, what is, let's derive the truth table. So A, B, and C would be A plus B. So what do you think? If A and B are 0, 0, what is C? My eyes are not that good. If you hold up fingers, 1, right? 0 and 0 would give you 0, then you flip or invert it, so you get 1. How about 0 and 1? 1 and 0? 0, but 1 and 1? 1 plus 1 would give us 1. So we invert it, output would be 0. So the result of a NOR gate is that the output would be high only when all inputs are low. So if you have a 3-input or NOR gate or a 4-input NOR gate, 5-input NOR gate, the output goes high only when all inputs are low. Okay. Output goes high only when all inputs are low. And there is an advantage and disadvantage to implementing both. Okay, you first and you next. Yes. So the question being asked is, in an OR gate, is it always the sum because we're using the carry bit? Yes. We are counting the carry bit in terms of the math. Yes, we are counting the carry bit. Yes. Yeah. Yeah. Yes. Okay. All right. Let's see. So there are similar to arithmetic rules, mathematical rules. We have some rules when it comes to this kind of math. Okay, this is known as algebra. It's known as Boolean algebra, known after, let's see, I thought I had this here. Okay, known after Boole, George Boole, known as Boolean algebra. As if regular algebra was not good enough, right? All right, and then there are certain laws that were named after a person known as De Morgan, so they come to known as De Morgan's laws. These are very handy when we're trying to build logic circuits. And if we keep these laws in mind, and we understand these laws, we can implement any kind of logic circuit using any kind of building block. Okay. So this helps us to create more efficient designs. Efficient would mean lesser number of components. That means we can fit a higher number of functions within a certain quantity of logic gates. First one up is the AND function. A and B can be written as A naught plus B naught naught. Okay, that's how we would read this. A naught plus B naught, the whole naught. Okay, and so that is an alternative form of implementing A and B. Okay. But let's pause and think about what it means. If you take the sum of two inputs and you invert it, you take the sum of two inputs, it's OR, and you invert it, it's a NOR, right? So this function right here, you have two inputs and you're inverting the output, is implemented with a NOR gate. But if you already have the inputs inverted, meaning you have a NOT gate and you apply an A input, you get A NOT as the output. Meaning you have two NOT gates and a NOR gate. Let's do a small illustration. So you have A, then you have A naught. This becomes B naught. And this output right here is A naught plus B naught naught. Does that make sense? And the result of this is that this is an AND function. And you can go through the truth table and look at it, and it'll match the truth table for an AND gate. And that's where these laws come from. Okay, so an AND function, A and B, can be implemented with two NOT gates and a NOR gate. Now it might seem counterintuitive. Why would you not just take one gate, and why would we need three gates? Right? That's a very good question. But this is simply a law that allows us to actually create multiple gates or multiple kinds of implementation using just fixed number of gates or fixed type of gates. Okay. So A and B can be implemented as A naught plus B naught, the whole naught. A plus B, the OR function. So this is the AND function. This is the OR function. The OR function can be implemented as A naught, B naught, sorry, A naught and B naught, the whole naught. Okay. So here you're using the NOR gate. Here you're using the NAND gate. And typically NAND gates are the ones that are fabricated. Where else have you heard the word NAND? You have come across this, I promise you. Anyone hear of NAND flash? You have come across this. You would have probably read it. When you buy USB flash drives, you buy SSDs. Those are all NAND flash memory types. And that's what it refers to, NAND gates. That storage memory that you buy, the USB RAM, it has the word NAND or the NAND flash in there. And those are NAND gates. They store digital data. They store digital data in the forms of zeros and ones. And the reason it's called flash memory is because you can wipe it with a flash of electric voltage, electric current. Flash memory. So if you look at your, don't know about laptops, but if you look at the specs for your laptop devices or anything, it will say NAND flash. And that's what it refers to. So you would have NAND logic gates, and you would be tasked with creating different kind of circuits using these logic gates. And so then you can use these mathematical functions to implement everything using just NAND gates. And that's where these kind of laws are useful. Okay. All right, so this was for 2 input. This is for 3 input. the logic remains the same. You can go from and to or, and you can go from or to and by using these laws. Okay, so A and B can be represented as a sum, or A plus B can be represented as a and or a product, simply by inverting. All right, any questions? Okay. All right, let's take a look at a couple more gates. These are known as XOR and XNOR. XOR and XNOR. The X stands for exclusive. So it's exclusive OR gates and exclusive NOR gates. The truth table for an exclusive OR gate looks like this. You have A, B, and then output C. This is referred to as A exclusive OR. Exclusive OR goes high when both outputs are different. So you have 0, 0, 0, 1, 1, 0, and 1, 1 for a 2-input exclusive OR gate. The exclusive OR gate states that the output goes high when the inputs are different. When the inputs are the same, the outputs go low. Okay, when inputs are the same, the outputs go low. An exclusive NOR is simply the opposite of an XOR or an exclusive OR gate. And so this is XOR, this is XNOR. And as I stated, this would simply be inverted. So C, exclusive OR, and not at the top. You have 0, 0, output goes high. If you have 0, 1, or 1, 0, output goes low. Okay. As a practical real-life example, let's look at our thermostats. You have these smart thermostats now. I mean, this one's not smart, but nowadays you have these smart thermostats. But even a simple thermostat, you set it at a temperature, right? Let's say that's input 1 or input A. That's your set temperature. And then input B would be your measured temperature in the room. So if both of them are the same, outputs either high or low, depending on how you want to design your system, then the system, I mean, the thermostat tells your heating or cooling unit not to turn on. If there's a mismatch between the set temperature or the desired temperature and the actual measured temperature, then the outputs are different. If the outputs are different, then it turns on. So that's where we would implement this kind of logic design circuit, right? You have a desired input and you have the measured input. Depending on which output you want, if there's a mismatch between your desired and your measured input, output either goes high or output goes low. And that kind of logic is implemented in digital logic design. All right, questions? Any questions? Okay, let's look at the next one. So, as I stated, sometimes all we have available to us might be just NAND gates or just NOR gates. Okay, so we can use them as building blocks. We can use them as building blocks to build different kinds of circuits. Okay, the easiest one to create with both a NAND or a NOR is an inverter. If you short the two inputs of a NAND gate, then the output is an inverter or a NOT gate. That's it. As easy. It can be implemented with like 2 transistors connected back to back. If you short the 2 inputs of a NAND gate, the output is inverted. And here's how. It becomes A and A because both inputs are the same, shorted together, and the output is inverted. So A and A is basically A. And so the output is A naught. A naught, inverter. Same thing with the NOR gate. Actually, it's right next there. You just short the inputs together, the output is inverted. All right. For a NAND to NAND to OR conversion, meaning if you want to implement OR conversion, so this is an inverter. If you want a OR gate created out of NAND gates, you first create an inverter, so you get A naught, and then B naught. And from De Morgan's laws, we can get A naught and B naught naught is equal to A plus B. So we get an OR output using 3 NAND gates. Okay, it's an OR output using 3 NAND gates. And you can easily do the truth table and verify yourself that it works. As an example, if I do this, you have AB, but both are shorted, so A equals B. So if you apply 0, 0, and you do an AND, and you invert it, you get a 1. If you apply 1, both inputs are 1 and 1, you get a 0. So the output is inverted. Right? Output's inverted. And you can do the same for this one too. And then of course, creating a AND gate would be rather straightforward. You simply take a NAND gate and you feed it into the NOT version of the NAND gate. So the output is simply A and B. So you can implement all 3 gates. This would be a NOT gate. You can implement all 3 gates and or NOT by simply using the NAND gate. Hence, it's known as a building block. You can use the NAND gate as a building block to create any other gates. Yes. Where? Here? Here. Yes, it would become A and B naught, which is the output of the NAND gate. But we are feeding it as input to this NOT gate. So it would simply become A and B naught. That flips the inversion. And so it's simply A and B. And we can go through the math to actually determine that to still work. right? Similar to the NAND building block, we can also use the NOR gate as a building block. The NOR gate, again, inverter. And so this is a NOT gate. This is a OR gate. And this is a AND gate. So simply by shorting the two input terminals, we get a NOT gate. We connect a NOT gate to the output of a NOR gate. We get an OR gate. And if we use 3 NOR gates, we can get an AND gate. So let's take a pause. You think over that. Let me know if you have any questions. Any questions? All good? So far, so good? It's going to require a bit of reading and studying outside of class. All right. Then I want to bring up, we won't go too deep into these today, but I just want to talk about combinational and sequential logic. Okay. Combinational logic is basically designing logic systems using different combinations of logic gates. Okay. So you're designing a system using different combinations of logic gates. And so that's where the laws are very useful. So you can implement, you might have a system, for example, multiple inputs. And depending on what you want to do, what you want to obtain as the output, you can design using Boolean algebra, combinational circuits. As I said, multiple inputs, right? So you have many, nowadays especially, you have these smart devices. Even our fridge is supposed to be smart nowadays. There are smart fridges that are available where there's a specific spot to put down a gallon of milk, and it senses the weight in the milk jug. Once it falls below a certain level, it triggers an input and it sends a, wouldn't quite say an alarm, but sends a notification to the app that tells you and adds it automatically to your grocery list that it's time to go buy some milk. So that's, well, that's if it works properly. As usual, security is not a concern for these manufacturers. So if somebody hacks into your fridge, you can turn it off. Now that's a separate topic. That's just an example of how convenient our life could become. Okay. It's not often that we would forget these kind of things, but again, we have smart devices. Depending on what kind of result we want, depending on what kind of output we want, depending on our application, we can design a logic circuit for that outcome. And that's where combinational logic would come into picture. We would use the math and we can design a circuit to do a certain function based on multiple inputs. And then there's sequential logic. Sequential logic requires a clock function, keeps everything in synchronous operation. And the clock function is basically simply the presence of input or the absence of input. So 1, 0, 1, 0. Okay. And we'll look at both of these in next class. Okay, so we'll stop class here today because the logic gates itself is a lot of material. So we'll look at the combinational and sequential logic beginning Friday. All right. All right, so we'll end class here today, and I will see you all on Friday. Yes. Yes, it's all digital signal. Yes.